this video, we're going to use VisMode to help us understand user-defined classes and objects. So first of all, we'll look at simply creating and using objects, but then we're going to turn to understanding mutation with objects, help using the visualizer. Our running example is going to be defining and using classes that represent points. Here, a point is a two-dimensional point with an x and y coordinate. I've run the code in VisMode and started it back at the beginning so we can single step. We define the point class, okay, and now we're going to define a point. Okay. So our first point here, P, well, what does it do? It goes into the initializer. The initializer says, oh, self is this 0.1 instance that we happen to be building right now. X is 4, Y is 5. Those are the arguments that we passed in. And it says, well, the instance that we're building up, X is 4 and Y is 5. And we're going to return, well, we don't return anything in init, but overall, this function 0.1, the creation function, the constructor function, which isn't really visible here, returns this instance that was just created, this object, and now P equals that. Okay, so we're going to do exactly the same steps once again here with another creation. Okay, that we're going to create Q equal to 4 and 5. Just happens to look alike. And, well, I'll assign R to BP. So it's another, it's an alias for this same object. Okay, now we're going to do some method calls here. And along the way, we're also going to be looking at what mutation is involved because we have some aliasing. Okay, so for p.setX, we call the setX method. Our argument is 10, and self is this object that P is. Okay. And so in the self_x body, it comes in here. Now we change x to be 10, well, self.x, which is p.x. And then that's it, we return. Okay. Notice that because of the aliasing, P and R, which are alias to the same object, they both have their x value changed. So now we're going to use these get x methods, the method over on several different objects. First, we call it on P. So self is this object because that's what P is. We return 10 and print that. And then we're going to do it the same thing with Q, except this is Q down here. And now we're going to do the same thing except with R, which is the first object, an alias for the first object. Okay. So through that, you can see what's going on here. In particular, that self truly is getting the appropriate object when we're calling a method, and that this init method is being called implicitly when we use the constructor to create and initialize our objects. Okay. In the previous example, part of it was that we were exploring mutation in conjunction with aliasing. We're going to look at another thing with mutation here in using a slightly different version of the point class. Instead of taking two coordinates, x and y, we're going to pass in a list of coordinates. So you can support 2, 3, however many dimensions you want. But in this example, we're just going to use 2. So let's single step through this code. We define our class. We are going to define a list here of coordinates, 4 and 5. Then we're going to pass those coordinates into point 2 so that in order to define P. So the coordinates, well, coordinates here is going to point to the same list, and self is this new instance that we're building. And coordinates of this instance are in fact that same list. Okay. So P here, if you notice the pointers, okay, their global coordinates points to this list, as does P dot coords is also the same list. We build Q, an object, exactly the same way, so that both P and Q are sharing this same internal list. Well, we can build up R passing in 4, 5, but this happens to be a different list 4, 5. So you can see here that R has its own state that it's not sharing with Q and R. And you can also see how the visualizer draws it differently. Okay. Now we can set the 0th coordinate, okay, you know, the x coordinate basically, of P. And naturally, that's going to change the shared state, thus changing Q, but not R, as we can verify when we get the coordinates of each of our objects. Okay. So once again, all that's really happening here is aliasing, except the difference is that we're sharing what is supposedly a hidden state, and we can change that hidden state from one of the objects or the other. Or in fact, if we had changed the global list coordinates, we would have changed the hidden state within P and Q. Okay. As we saw, when objects share state, when you change one object, you can change the other. Now, that's okay, but it's typically not what you actually want. So how can you avoid it? Very simply, just copy the data. Here in our initializer, we're copying it using the list function, and let's verify that. We define our class, our global coordinates, we create P, and notice that it has its own copy of the list of coordinates. When we go and define Q, it also gets its own copy of the list. It's not shared with the global one or with P. So when we completely run it and get the coordinate change, one of the coordinates, and print all of them out, we see that we've only changed P's copy, not Q's or R's.